The answer to the Himalayan 450's low end torque problem lies in its bore and stroke. On paper, when you compare the spec sheets, both these vehicles are putting out around 40 Newton meters of torque. You'll see that the torque also goes up. This is why your Royal Enfields were very good at delivering low end torque. These are the kind of choices or engineering designs that can lead to the chassis failure. Today, I'll help you break down the Royal Enfield Himalayan 450, the engineering and design decisions that have affected the product. If you've ridden the Himalayan 450, you would have observed a couple of things. One, it has great suspensions. The chassis is great. It has great capability to munch miles on the highway. But the low end torque for the city is pretty bad. Today, I'll help you break down the Royal Enfield Himalayan 450. We will look at the engineering and design decisions that have affected the product. And with this, I hope you get a better understanding of why the Himalayan 450 does what it does. This is something I'm trying out for the first time, and I hope you like it. So let's start with the engine. The Royal Enfield Himalayan 450 has a power output of around 40 horsepower and a torque of about 40 Newton meters. And this peak horsepower is coming at around 8,000 RPM. And this peak torque is anywhere at 5,500 RPM. Now, these are something that you would read off of specs, and there is no value add in you knowing this. But I'll tell you some interesting aspects that you should know as customers. So let's consider this torque versus RPM curve. Now, consider there are two bikes. Both have a peak torque of around 40 Newton meters. But one bike can achieve the 40 Newton meters somewhat like this, where you have your peak torque coming in at around 3,500 or 4,000 RPM. And let's consider the Himalayan, which could be doing something like this. Now, on paper, when you compare the spec sheets, both these vehicles are putting out around 40 Newton meters of torque. But there are two things that we'll have to specifically understand. One, at what RPM each bike is putting out the peak torque, because lower the peak torque, better your low end torque. And second, what is the area under this torque curve? Now, this is a direct indication of how much drivability you have. For example, if you are opening the throttle slightly, how much is the bike propelling? So this indication is given by what is under this curve. On similar lines, you have your power versus RPM. So the bike has around 40 bhp of power, and this comes at around 8,000 RPM. Now, something that I'm sure some of you guys are aware of it, I'll give you a quick differentiation of what is torque and what is RPM. Now, torque is something that is called a turning power. For example, if I have to move an object, let's say there is an object here. If I have to move this object from this point to this point, I'll apply a force. Now, this force can move this object from here to here. But let's say I have to keep the object in the same position, but I will have to turn it. Now, if I have to turn it, I can turn it like this, or I can connect a rod or a linkage to this and turn it from a distance. As the linkage distance goes up, the effort that I would be requiring to turn this object will reduce. Now, that is an indication of what a turning power or torque is. Not turning power, but what torque is. Now, just like how the example I gave you, the wheels are turned by the power of the engine. There is a torque that is generated at the engine output shaft, and this output torque will actually turn the wheel. Now, torque is a direct indication of how much turning power is available at the wheel. Now, if this is clear, now let's move on to what is power. So, power is basically an indication of at what rate can I deliver this torque. For example, I told you that I can create a linkage or a lever like this and turn this object. Now, let's say I am already turning this object at a certain pace. Now, if I have to turn it faster, at what pace can I turn it at the most? Now, that is an indication of power. So, at what RPM, what torque you get, the factor gives you power. In simple formulas, it is basically 2 pi nt by 60, where n is your RPM and t is your torque. Now, this is power. This is slightly technical, I understand, but I will break it down and I'll explain why this is important in the further sections. Now, if this is clear to you, let's also look at the bore and stroke of this engine and why bore and stroke matters. Before we move on to the next section, I would like to take a moment to share something with you. 98% of our viewers have not subscribed to our channel. It will cost you nothing, but it will keep us motivated to bring the best automotive content in front of you. If you have gained any value out of this video, please make sure to hit that subscribe button. And on the answer to the Himalayan 450's low end torque problem lies in its bore and stroke. Let me explain how that works. Now, the Himalayan 450 has a bore of around 84 mm and it has a stroke of around 81 mm. Now, bore is basically the width of the cylinder and stroke is basically the distance that the piston covers in delivering the torque. So every time there is an explosion, the piston moves downwards, and when it moves downwards, there is a certain distance that the piston travels. So the total travel is basically the stroke. Now, the combination of or the product of bore and stroke gives you the cubic capacity of the engine, and this product is basically equivalent of 450cc. Now, 450cc is basically slightly less than half a liter of water. If you take a half a liter water bottle and if you chop out 50 ml from it, whatever is left, now that is equivalent of a 450cc. Now, Himalayan has 81 mm of stroke. So if I just draw what it looks like, there is 81 mm of stroke here and about 84 mm of bore. Now, there is a reason why you will see the KTM engine here. We'll get to that in a bit. Now, this construction of an engine where the bore is wider than the stroke is called an over squared engine. So if you take a square, which is basically equal sides on all four sides, and if you stretch it wide, you get an over squared engine. Now, the opposite of this is an under squared engine, where you take the same square, elongate it. Now, this kind of engines have higher stroke lengths, and this kind of engines have a wider bore. Now, if you look at the Royal Enfield Himalayan 450, it is very close to being a perfect squared engine, but it is slightly towards the over squared side. Now, what this does is, let's take the example of the previous Himalayans. Like if you take the example of the Himalayan 410 or any Royal Enfield for that matter, you will see that the stroke length is longer than the bore. Now, this is why the previous example that I gave you becomes important. Basically, if you have a lever arm like this, and if your lever arm is longer, then it is easier to turn, correct? Basically, your turning force increases. The same thing happens with engines which have longer stroke length. Now, longer the stroke length, let's say this is your crank. When you have an engine which has a longer stroke, now this is your rod that connects the axis to the piston center. Now, this distance will go up. Now, when this distance goes up, you will see that the torque also goes up. This is why your Royal Enfields were very good at delivering low end torque. Exactly why the Himalayan 450 is slightly worse than the previous Royal Enfields in terms of low end torque delivery. Now, KTMs are examples of over squared engines where they have shorter stroke compared to its bore. Because of this, you will see that these kind of engines are capable of running at higher RPMs. So if you have an over squared engine, the RPMs can be higher. And if you have an under squared engine, the RPMs are shorter, but it delivers more torque. So in order to get the best of both worlds, this is why Royal Enfield has gone with a slightly over squared engine where it can rev up to higher RPMs, which gives you better highway cruising speeds. And they've compromised slightly on the stroke, but not enough to make it a high revving engine, but not low enough to make it an engine which has good low end torque. This is why the Royal Enfield has that kind of a character. Now that you have understood how the engine performs and how the design decisions on the engine affect the overall drivability of the bike, let's look at the ergonomics. Now, ergonomics is better to be understood before we get into handling and comfort, because a lot of factors that affect comfort are predominantly affected by the ergonomics, and then your suspensions and other things come into play. Now, there are 3 points marked here. This is your handlebar point, and this is where you sit. We call it the H point, and this is where you place your foot. Now, these 3 points form what is called the rider triangle. Now, these rider triangle come in three different shapes. One is in the case of a cruiser, where the foot point is ahead of your seat H point. This is your handlebar point. So the foot point is actually ahead of your seat point. Now, in cases like this, you will see that there is a lot of force that goes on to your seat because your back is now supporting the whole weight of your body, and this will cause you painful sensation, especially on the lower back. So this is why cruisers generally give you back pain, although they are designed to munch miles. In reality, they are only comfortable for shorter ride distances, and this is the reason why. Now, the next example is the case of a sport bike, where let's say this is your seat, this is your handlebar. In case of sport bikes, the handlebars are slightly lower. This is done to ensure that your center of gravity is lower. The lower that you push this point, the more you bend forward, and while bending forward, you also bring your overall center of gravity down. And your foot position is somewhere here, so that the overall triangle supports you to steer the bike better and roll the bike better. Now, what Royal Enfield has done is something that is more towards the comfort side for sure, but in a way where you can spend more time on the saddle. This is the genius at play, where the foot position is slightly ahead of your seat H point. Now, in case of the Royal Enfield Himalayan 450, if you have taken a look at the review video as well, I've explained how you can stand on the foot peg and do a proper squat, pick yourself up, go to a standing position and ride. All of this while not touching the handlebar. It is that easy on this bike. Now, because of this, whenever you're going over rough patches or rough roads, your body will automatically distribute the load between your foot and your butt in a way where you can spend more time on the saddle. This is a good design decision by Royal Enfield and one of the major drivers of the comfort on this bike. Now that we have discussed about the engine, the ergonomics, let's also look at the chassis and why the dynamics of the Royal Enfield Himalayan 450 is the way it is. Now, a couple of interesting design choices and engineering decisions here, where the headlight is not connected to the handlebar. If the headlight was connected to the handlebar, then the overall handlebar would have felt slightly heavy, which will have impacts when you're cornering. When you're leaned in, let's say your headlight is also connected to your handlebar, there is tendency of the steering dropping more and more into the corner. This can sort of unsettle the front. But on the Himalayan 450, this choice is a good one. Now, let's move on to the engine. There are some interesting things happening with the engine mounts. So there is one engine mount here, and the chassis is connected to the rear part of the engine somewhere here. There are some very critical aspects here. For example, if you take a look at the mounting points on the KTM, you will see that there is one mounting point here and there is a second point here. Now, why this is different over here is basically, if you had an equivalent mounting compared to the KTM, the first mount should have been somewhere here and the second mount is more or less similar to where it is today, or probably higher here. Now, this creates a different kind of loading to the engine. Now, on constructions like this, the engine is used as a structural member. So engine becomes part of the chassis. But the interesting aspect is, now the way the engine is getting loaded, when there is a load that comes onto the chassis like this, let's say the vehicle goes over a bump, the bump is transferred like this, which turns and loads the engine in this direction. Now, if you see what is happening to this mount is getting pulled. This is not the right way of loading the engine, if you ask me. Whenever, let's look at the mount alone. Let's say this is the engine and this is the mount. The mount is the most fragile when you're loading it in this direction. Essentially, you should have loaded the mount in this way, or have the mount at an angle like this and then load it in this direction. So essentially, you have to pull or push the mount, but instead we are bending the mount. And the engine is also a cast component. So because it is a cast component, this kind of loading is not always preferred. Now, fingers crossed, these are the kind of choices or engineering designs that can lead to the chassis failing. Now, whether or not this was the reason for the latest or the recent mount failure or the chassis failure that we've seen, I'm not sure. It could be a one-off quality concern. Are there ways in which this can be mitigated such that there are no failures? Definitely. You can actually over-engineer this part of the engine and get away with it. Is it the most efficient way of design? In my opinion, maybe not, but you need not take my word for it. If this is clear, now let's move on to the comfort and how the suspension is tuned on this vehicle. Now, on a KTM, you would have seen the rear suspensions somewhat at this angle. But over here, the angle is much steeper. Let me explain what this does. Let's say this is your wheel and this is your swing arm. The swing arm is connected to the front swing arm axle. Now, if a suspension is in this angle, let's say the wheel moves up by about 10 centimeters, hypothetical scenario. Now, this would probably move by around 3 centimeters. Correct? 3 centimeters. Now, the ratio of this to this, which is 3 by 10, which is around 0.3 or 30%, is something that is referred to as the motion ratio. So, what is the motion of the suspension compared to the wheel? So, if the wheel travels by 1 mm, the suspension travels by 0.3 mm. That is what essentially it means. Now, as you start decreasing the angle, making it more and more steeper, this 3 mm or this 0.3 as the ratio keeps dropping. It might become 0.2 or 0.25. Now, what this means is, let's say your front suspension, the Royal Enfield has a longer travel suspension on the front. And let's say the front suspension has a travel of 150 mm. Let's say this is the front. The rear should also have similar travels, let's say 120 to 150 mm. If not, the vehicle will always have a pitching motion. The front wants to travel more, the rear travels less. So the moment you hit the front and then hit the rear, the way the overall bike settles will differ. Now, to get both the front and rear suspensions in sync, Royal Enfield has done a very good job here, where they've introduced something called a linkage mechanism. So linkage mechanism is something that I've explained here, where this is your conventional travel suspensions, where let's say 10 mm of travel here will result in a 3 mm travel here. But over here, there is something that is different. Now, when there is a 10 mm travel here, the suspensions will move up. There is a linkage here, there is a linkage here, this is your swing arm. With this 10 mm motion here, you're creating an extra lever which will give you additional travels. So instead of traveling 3 mm as it should have before, you will probably get 4 to 5 mm depending on the geometry of the linkage. Now, with this brilliant idea, what Royal Enfield has achieved is they've tried to match the travel on the front with the rear as well. Now, because of this smart engineering choice and with good tuning on the suspensions, both the springs and the dampers, they've been able to achieve good travel and good comfort. Since this is a new form of video that I'm trying out, I'd like to keep the overall video as concise as possible. There are a lot of other attributes that we can talk about, but I will not be talking about those things in this video, and we will end it with the design of this vehicle. Now, when people think design, this is something that is subjective, and there are designers who are trying to understand what appeals to the customer, and there are choices of shape and color, and there are a lot of psychological things that are in play which will affect your overall decision making. I'll give you an example of this. Now, consider this bull over here. In the side view, the Royal Enfield Himalayan 450 has certain resemblance towards a bull. For example, there is this curve or line that is there that you can see here. There is a short tail bit that is similar here. And there is a muscular stance of the bull that is seen on the tank. Now, a designer is constantly trying to show you something with shapes and forms, and these are the kind of elements that will attract certain kind of crowd. So if you are somebody who likes muscle, these are elements that will also attract you on this bike. Now, this is coupled with a round headlamp. Now, anything that is round will actually try to tell you that, okay, I am harmless. And since all Royal Enfield headlights also are round, it will still make you remember that, okay, this is still a Royal Enfield. Now, a round design will actually say that you're safe, you are with me, I will not harm you. And lines that are sharper will actually tell you that this is more aggressive. Now, there are no sharp lines per se, but there are hints of sharpness, which will actually tell you that there is some amount of aggression with a lot of muscle. Now, the muscle can be indicative of the torque and the capability and the grunt of Royal Enfield. And the sharp lines can tell you that, okay, there is a bit of agility that is there. Now, there is always a mix of feelings that a designer is trying to give you. There are more than one thing that a designer wants to convey. And this will generally come out in the form of the design lines and the kind of volumes they will. Now, with this, I will end this video. This is a new tire, like I've mentioned before. And if you guys like this kind of video format, let me know in the comment section. And pick a bike that you want me to break down next, and I will do a video on that. Thanks for watching this video until the end. If you have enjoyed this video, be sure to give a thumbs up. Let us know how you felt in the comment section. And do not forget to subscribe to our channel. I'll see you again in the next one. Until then, ride safe and Godspeed.